Hello friends, welcome to the Boolean Brain. In continuation to the LeetCode Daily Challenge series for the month of January, we have covered so far 22 days challenge. We are on day 23. Let us try to solve today's challenge. Okay, the title says minimum pair removal to sort array part 2. So we have given an array nums. We can perform the following operation any number of times. Select the adjacent pair with minimum sum in nums. If multiple such pairs exist, choose the leftmost one. We have to replace the pair with their sum and return the minimum number of operations needed to make the array non-decreasing. An array is said to be non-decreasing if each element is greater than or equal to its previous element. Okay, so if you're following the series, yesterday's problem statement, that is day 22, was also on the similar lines. Exact problem statement was same. It's just yesterday's constraints were less. And if you observe, today's constraint must be higher. So the nums of length reaches till 10 power 5. So the yesterday's problem statement where we had went ahead with the brute force approach, I was kind of expecting this. Hence we had coded the brute force approach in the yesterday's video so that we can discuss about the optimal solution in today's video. Okay. So problem statement is exactly same. We just have to optimize it. So let us try to um, optimize this with the help of yesterday's approach. So if you are observing that in yesterday's brute force logic, what were the things that we were doing? We were checking, we had a while loop. We had a while loop, and the while loop was running until we do not have a not non-decreasing. Means until we find a increasing array we will keep on iterating, and at each point we were getting this sum, we were finding the minimum sum and replacing it. So finding the minimum sum was O of n and replacing was again O of n, and this was again going O of n. So this O of n into O of n was going to O of n square. So cannot accommodate we cannot accommodate the and square in today's problem because constants are 10 to the power 5. So how should we optimize it? How should we optimize it in order to fit or satisfy today's constraints? So considering this is 10 power 5, the accepted solutions are O of n or O of n log n. Okay, cool. Now, I had mentioned in the yesterday's video as well. In we want to find the minimum operations, and we at each position we have to find the minimum sum. So whenever minimum sum or minimum element or maximum element in some array is given, we have to first think of priority queue. So priority queue is the heap implementation in C++. Actually, it is the internal concept is nothing but heap. So since we want minimum, we have to use minimum heap. So prior knowledge of having minimum heap is essential. So what a min heap is? So min heap is nothing but a data structure which somehow stores the element in such a way that the top element always gives us the minimum when we are working with min heap, and it gives maximum element at the top when we are working with max heap. Okay. Cool. So that's the one hint that we should understand from reading the problem statement. Now, there are three things to do. First thing is we have to check, we have to keep iterating until the array is sorted. Okay. And the next is finding the minimum sum each time. So for finding the minimum sum, let me bring this here. Okay, cool. So So this was the brute force approach. Now we are trying to optimize this. Okay. So we have to find the minimum sum. So for this, we should think of some solution involving heap. How we will discuss it further, but let's first try to understand how the concepts will get introduced. So for finding this heap, And in order to find an element, the heap operation is like the heap operation, we can basically, uh, work in log n times, because heap internally, the operation that we can do are in O of log n, like the insertion, the deletion, the like, since it's a queue, the element stored at the front can be popped up easily, and the heap internally heapifies. That operation is log of n. Okay, cool. Now we again had to replace the minimum sum. Okay, so if we somehow store all the sum of adjacent elements, somehow store the sum of adjacent elements into this heap, we have to also replace the minimum sum so the adjacent changes. Okay, so we have to basically update the heap as well, right? Apart from that, we were having another loop. So again, this can happen using heap, adjusting heap. Okay, and there was another loop where it was checking array is not decreasing, right? So we were having a loop starting from 0 to the end and checking if the array is non-decreasing. Non-decreasing means it should be sorted array. Okay, each element should be greater than or equals to previous, that is non-decreasing. So for calculating this, we were earlier going on O of n, but we have to do this somehow by reducing this. We should not be in a position now to calculate this each time. So in order to do that, what we can do, we can first keep a track of all the all the uh, bad pairs. So we can first check how many bad pairs are there. So bad pair is nothing but a pair in which the next is smaller than previous. So 5 comma 2 is a bad pair. Why? Because the next element is smaller than the current. So it's a bad pair. So if we somehow keep a track of all the bad pairs, and after doing some logic, we try to fix each bad pair, and at each position we can basically reduce the total bad pairs, right? So that's how we should be able to optimize the O of n loop. Okay, cool. So now if we are using this in O of bad pair, so this O of n is reduced, and this is operation is going log n times, now finding the minimum, and this is happening for all the n. So because at max n minus 1 bad pairs can exist in case the output input is something like this. It's a reducing, right? So it's strictly decreasing. We have to basically make it increasing. So how many pairs are there? 5, 4, 1, 4, 3, 2, 3, 2, third pair. So total 3 pairs. So at max n minus 1 bad pair exists. So we have to outer loop will range of n, and this at each position we are doing this log n operation. So overall time complexity should come around of n log n. Okay, cool. Now we understood the approach. Now let us try to think, how can we fit this approach? How can we use heap? How can we use these bad pairs? And how can we adjust heap to obtain the solution? Right? Cool. Now, if you let's start from the start. So the problem statement is a bit lengthy, implementation is a bit lengthy, so I'm not coding it live with you. I'm just trying to explain you the solution. Okay, so this is the nums that we are given. So I calculated the total size in n. Now I declared another temporary array of type long long. So this is a way to change the type of int to long long. So why did I change the size? Because I want to store I want to store the sum of elements. And if you see the constraints, each constraint can go up to 10 power 9. So if I make a sum of two elements, then it should not exceed the int range. That's the reason I increase the int range to long. Okay. Now I'm feeding my temp is initialized with all the elements from the nums. So this is basic type conversion. Now, as I mentioned, we need a mean heap, right? We need a minimum sum at each point. So a mean heap is declared. So in C++, mean heap implementation is using priority queue. We declared a priority queue of type pair. It's a pair, so we will store the sum in here and the index at which the pair exists, sum exists. So 5 comma 2 is a pair. So 5 plus 2 is nothing but 7. 7 exists at 0. So that information we will store here. Next, we need a container storage. This is part of a syntax, and we need a greater pair. We can also use a custom operator. So this is part of uh, declaration of a mean heap in C++ using priority queue. Okay, cool. Now we need, so I had a priority queue now. So I'll explain the usage of next and previous afterwards. First, what we need to do, we need to ensure we want to find all the bad pairs. What is a bad pair? If the next is less than the current, it's a bad pair. So I start a loop right from 0 to n minus 1. Why n minus 1? Because at I'm checking current and current plus 1. So n minus 1 and I plus plus. So I check if the ith element is greater than the next element. That means it's a bad pair. So I increase the count to bad pairs. Also, I'm pushing the sum of ith and the I plus 1th element into the priority queue. Why we are doing this? Because we initially want to feed the queue with the sum of each adjacent, like 5 plus 2, 7, 3 plus 2, 5, 3 plus 1, 4. So that information we want to populate in the priority queue. So when we push here, our queue will, for this example, for this example, our queue will look something like 5 plus 2 is 7, 3 plus 2 is 5, and 4. So the list is basically 4, 5, 7. So that's how, so it's a queue, right? So the front element is always the minimum. So that's how a queue would be implemented, priority queue. Okay, great. Now I'm starting the loop because we want to do this operation. We want to do the operation until all the elements are sorted. When the all elements will be sorted, when this count reaches 0, the given input becomes sorted. Okay, so that's the reason for having the while loop until while the bad pairs count is greater than 0. Okay, cool. Now, now we in the first iteration we are in this loop. It means we have at least one pair which is a lazy bad pair. So we would want that pair. Let's say if this is the input and we saw that the current bad pairs exist. Okay, current bad pairs exist. So we basically popped the top element. So priority queue dot top gives us the top element and pop removes the element from the queue. So we first fetch the 4. We don't not just fetches the 4. 4 gives 0, 1, 2. So it's 4 comma 2. It's a pair, right? Similarly for 5 comma 1 and 7 comma 0. Okay, so these are the pairs how the way it is stored. Okay, now we fetch the top. We now now we want to find a valid adjacent alive pair because because yeah. So if you see here, what is the action that we can do? We we have to find the minimum. So this is the minimum, right? So this 3 1 is the minimum. Now and we have to basically store 3 1 with 4. Okay, and basically make this place vacant. Okay, and make this place vacant. But if we make that vacant, if we make that vacant, the erase operation on the array will itself cause O of n. That's the reason we will not erase this. We will keep it as it is. We will keep it as it is, and we will have another array alive. We will have another array alive, which is declared here. It's a Boolean vector of exact same size. Initially, all elements are present, all indexes exist, so it is filled with true. Okay. Now, while popping the element, while popping the element, my first, so the first and second, right? Top dot first, top dot second. Top dot first is nothing but the sum, and top dot second is nothing but the index of the first element, isn't it? So I stored 3 comma 4, right? So the pair was 3 comma 1. Out of that first element, the sum is nothing but 4, and the first element, like this position 0 1 2, this position is stored in second. So this becomes the first. Now I declare first. Now my first is assigned. Now I need to check, I need to have this while loop carrying until the first element is not alive. Means not of alive first, it means if this element, if the alive vector is stored as false, it means that element doesn't exist. It's a dead entry, right? It's a dead entry. So in that case, I need to continue. But if this condition is false, it means it is true. The element exists, so we can move further. Now, for this element, if I'm working on this element 3, I want to find the second pair. Like the second pair is nothing but the next. So in order to obtain the next index, we have some index, if you want the next immediate index, we are storing that in the next index. So you I had created and declared this next index and previous index as well, because this store for a given I, it initially stores with I plus 1, and for a I it stores with I minus 1. Because you, you might ask, if you're just simply storing the I plus 1th and I minus 1th, why do we need these store arrays? We need those arrays because later on, when the comparison happens, when 3 1 pair is replaced with 4, the index is lost. Similarly, let's say this pair is compressed 3 comma 2 comma 3, and we got 5. So now this 3 is basically lost, right? So we deleted 3. At that point, update I want to update the next element to this, right? My now 2 is pointing to 1. And why am I doing this? Because in the brute force approach, we were replacing the sum and removing the entry. So the removing the space was itself carrying O of n. So to reduce that, what we will do, we will simply use the next index and previous index arrays to store the next and previous. Okay, it's like having the linked list and deleting a node in a linked list. Okay, cool. Now here we found the second pair. We found the first here, we found the second index here. Again, the second index, for that condition, we need to ensure the second should be greater than equals to n, or if it is not live, it means it's a dead. The second is reaching out of our range, because second was basically storing the next index. So next index for the last is basically the nth, like the range. So that's the check that we have, and ensure if this is either of the condition becomes true, we should simply continue popping the elements back. Okay. Now, again, like why are we doing this? If you're not clear, you will understand this once we go through the next part of code. Okay. Now, if the sum and if the sum of first, now we found the pair, right? We found the pair. If we found the pair which has the least minimum sum, if that sum, you remember we initialize the sum here. If the sum is not equals to first and second, it means that that pair is not matching with that condition. Again, in that case, we should continue. But if we found a pair, the first and second, these are the indexes, guys. Okay, first and second are indexes. The element existing in those indexes, if the sum is adding equals to sum, then we should basically break. Our code reaches here and we simply come out. Okay, now this is basically the lazy deletion. Okay, because our priority queue was storing the deleted elements as well, right? Once a pair is compressed, we don't update. Let's say this pair is compressed, we don't update the previous and the next pairs. That's the reason we have to do this in lazy deletion stage. Okay, cool. Now I have the pair with me. First and second is nothing but pair. Okay, I will write this like first, second. Now I want element next to this, and I want element left to first. Second, right to the second, and left to the first. I want this pair. So how can I find? Simply my second uh, is nothing but the next element of first, the next index of first. If I make, I get this second. And in order to obtain left, I can do previous index of first, correct? Now, right similarly is nothing but next index of second. Cool. Now, what are we doing? In each stage, in each bad pairs, if the code is reaching here, it means we are working on the first bad pair, first and second. So we simply check if the first is greater than second, it means it's a bad pair, isn't it? We simply reduce the count by -1. Why are we doing? Because we are processing the current bad pair, right? So our count is reduced. Okay. So okay, where was our output? Yeah, here, right? Cool. So input was 5231. Okay. Yeah. Cool. And the okay. Okay, let me carry everything because that would be a little easy for understanding. Okay, cool. So the least pair was 4 and starting from index 2. So 0, 1, 2. And left, first and second are these indexes, and left and right are these. So 2, 3, 1. So the pair in question is 2, 3, 1, and nothing else. Okay, so it's the end. Now, what we need to understand here, we basically, we basically are compressing this, isn't it? We basically are compressing this. So, so I need to check this condition. If my left is greater than first, if my left, what is left here? 2. If left is greater than first, what does it mean? It basically means earlier it was a bad pair. Bad pair of what? Left and first. I'm since I'm processing this pair, my if I'm processing this means putting 4 in place of this, the other subsequent pairs like associated to the left of 3 and right of 1 also gets affected, isn't it? So I need to basically take care what is the impact on the left and right in terms of bad pairs. Is the bad pair increasing when we substitute 4, or is the bad pair count again decreasing, right? So that's what we want to check. So if the is greater than first, left is greater than first, in which case it is not. But if it was such a case, so earlier it was bad pair. Now I want to check if the current left, which is 2, is less than, if 2 is less than equals to addition of first and second. Why I'm adding temporary first and second? Because this is what it is going to replace, isn't it? This is what we want to replace it. So I simply check if my left is less than equals to this, it means after substituting this, my bad pair count is decreasing. Earlier it was bad, and if this condition is now existing, our bad pair counts is decreasing. So I simply again reduced another one bad pairs. I So this is one, definitely one pair is going to reduced, but at the same time, considering the impact on left, we decrease one more time here. At the same time, we check if left the left element is less than equals to right. It means earlier it was a good pair, isn't it? If left is less than uh, first, it was good pair. Now, if the left becomes greater than the sum of first and second, if the left becomes increased, because this is also possibility, right? Because we are just compressing these two. Now we need to check what's the impact here. If it was a good pair earlier, what's the impact when these are compressed? If this was a bad pair, what's the impact now? So that's what we are doing. If it was a good pair earlier, and if this condition is satisfying, it means we are introducing another bad pair. So we increase the bad pair simply one. So we are decreasing first because definitely one pair is reducing. So count is initially decreased. But since we are introducing one more pair, which was earlier not counted, we increase the bad pairs. Again, we added this condition left greater than 0 because for the extreme left element, this position, the previous element is nothing but -1. So there is nothing to check on here. So simply to not go out of range or boundary, we first check the left element is greater than equals to 0. Then only we check this. Cool. If you understand about this part, you will easily understand the right part. Now, in right boundary adjustment, we check since right is moving forwards, we check if right is less than n. That's when our right index lies within the range. Now we check if right is greater than equals to second, right? So right is this part. Let's say in this example it doesn't exist, but let's say if this existed like this, some arbitrary case, if right exists and it's greater than equals to second, it means it's earlier it was a good pair. If it earlier it was a good pair, now right and if the right is less than equals to this addition of these two elements, then again it is satisfying as a good pair. Then we basically increase the bad. increase the, sorry, I think I mistook. If my right is greater, if my right is greater than second, and now right is less than this. So earlier it was good, now it was a bad pair. So we increase the bad pairs. Okay, because right should have been greater than the sum of these two. Cool. Now let's talk about the other opposite case. Now if the right is already less than the second, the right is less than second, it means earlier it was a bad pair, and earlier it was a bad pair, but whatever we are substituting now, if that is less than equals to right, if the substitution is less than equals to right, that's what we want, right? We want in sorted array. So if this condition is satisfying, it means it is reducing one bad pair. So we simply reduce one bad pair count. Cool. Now we want to basically add this. Like we have to merge this, right? The second is getting added into first. So simply we merge second into first. How we do it? We simply add the second element in the first position. If this was a pair 3 comma 1, we add 1 in this place. We are not doing anything of 1. We are not erasing. Why we are not erasing? Because erasing would have given us extra O of n. So we will keep it as it is. We will simply update the next and previous index, so that now instead of next 3, 3 is next pointing to 1, it will point to 8. So we will, this position will be simply ignored. Okay, that's the idea. Cool. Now we, the and another way to update or track the position is keeping this alive Boolean array. We will definitely we will store the value of that second index as false, means it is no longer alive, it's a dead index. Cool. And we want to uh, track the pointers correctly. The next index of first is now pointing to right. Why right? Because right was this was first, this was second, and this was right. So this first should point to right, right? So my first, the next index of first is pointing to right. We skip the second. Now we will check in order to update the previous index. In update order to update previous, we have to check care of the special case. So right, previous of right is nothing but first. Why first? Because this is the right, and previous to this, it earlier it was this. So we want to skip this and point to 3. 3 is first. So previous of right is first. So that's what we are updating. And why we added this condition again? Because our right should never exceed or be equal to n, because right is moving forwards. So we always operate, whenever we are operating, we will add this condition. Okay, cool, perfect. Now we have to basically update the new adjacent, push the new adjacent pairs. What was the new adjacent pairs? So the sum of new admission, like for example, for example, uh, left and first. Yeah. So this was the pair that we wanted. So the left element was 2 and the right was 8. So now we want to merge this 4 with 2, because this is the new pair, isn't it? After compression. Similarly, this 4, when compressed, it will form another pair with this. So 4 and 8, and 4 and 2, 6. So these two pairs. So I will check if left is again in the boundary. If it is greater than equals to 0, it means I need to push one more valid pair, which is left and first in the position of left, because this is where it is updating. Similarly, right, checking the boundaries, we update first and right. Okay, we are updating on first position here, and we update first and right element, isn't it? So this basically contains this position earlier contains first and second, right? So if you remember, we were storing that in first position. Now first contains sum of first and second, and we are combining with the right in one pair. We are combining with left in one pair. Okay, so that's how two more elements are pushed into our queue. So if you early remember, when earlier this was the queue, earlier this was the queue, right? 4251 and 70. When we popped this, so this 2 3 which comprised of 5 1, it is no longer valid now, right? But it is still present in the queue. This pair, when this pair is merged, because this pair was comprising of 2 3, now 3 doesn't exist. What exists is 4, but this 2 3 still exists in this queue. We have not popped it yet, hence, but we have the index here, which is 5 starting from 1. So we have the index here. So in order to nullify all such invalid pairs uh, after merging, we simply have this lazy deletion loop where we first fetch the elements, check the sum first, and all these skip conditions exist. If any of the uh, condition exists, we simply pop and move it further, right? So that's how we are maintaining the unnecessary pairs. Okay, so so new elements are pushed, and we at the end we simply increase the operation. This operation is running at this entire while loop. Sorry, not this while loop condition. So each such operation is increase operations, and at the end we simply return the operations. Cool. Okay, great. I hope I was able to explain this. This is a bit lengthier and challenging problem. That's the reason it's marked as hard. And until and unless you come across such problems, you will not be able to write this if you're solving this in the first time in the interview. So it needs practice for sure. Okay. Let us quickly, yeah, sample are passing. Let's try to submit and check. Yes. So it's successfully completed and we have maintained a streak of 23 days so far. Okay, cool. I have already explained the time complexity. Let us also discuss about space complexity. So if we remember, in terms of space, we are using using one priority queue. We are using next index, we are using alive, we are using previous index, all comprising of size n. Similarly, this is containing sum of all pairs. So again, going to O of n. So space complexity would be order of n, and time is order of n log n. I hope I was able to explain this. If you have any queries or doubts, please do let me know in the comments. And if you are new to the channel, please consider subscribing. Thank you for watching.